everyone, so I'm Sara Nasir, and today me and my teammates Taha, Jabbar, and Shahram Shafiq will be presenting our Discrete Structures project. And the title of this project is CPI Similarity Network Analysis for Pakistani Cities. So basically, first of all, talking about our source of data, it was from Pakistan Bureau of Statistics. And so this website basically publishes monthly data of CPIs for each city and for each category available in Pakistan. And so the first part of our project was first collecting this data in a proper form that we need to process it using the discrete structures concepts. So what we did was we extracted the 24 PDFs that we had for each month of each year from 2023 to 2025 that were available on the website. And then what we did was we organized the data into a CSV file, which had all the CPIs and all the cities and all their the monthly CPIs and their dates and names. And then we had to basically categorize them according to the categories mentioned in the project document. So we used Python code for that, and that helped us basically extract the data in a form on which we can apply different mathematical calculations and computations to actually come to a conclusion. So what the whole goal of this project is to basically use real data to derive how each city interacts with each other in an economics hub, and how what their relation with each other is, and how important each city is when we're talking about a whole economic hub. So first of all, coming to the mathematical model that we extracted each city's vector for each year as it's seen here. So basically our code made 12D vectors for each city in each year and in each category, and I wrote them into a text file so we could see exactly what the vectors look like. As you can see on the screen here, they look like something like this. These are 12D vectors. And then so we did some computations on this data. We calculated the cosine similarity for them, which is like a mathematical formula. And then we had set up three different thresholds, the tau values, which were 0.7, 0.6, 0.7, 0.8, and 0.6. So the lowest value basically helped what we derived from that is that each city is very closely connected whenever we set up the threshold value as 0.6 on our code. And whenever we set up 0.8 on our code, then that would basically lower the similarities between the countries, because we have increased the value of the threshold above which we consider the cities to be similar. And after this, we made a visual representations of each city's graphs and how they basically are similar to each other in terms of the cosine similarity as seen here, which Sharon will later be elaborating on as well. Like something like this. We extracted this using the cosine similarity. So now I'd like to call Sharon to elaborate further on the visualization and interpretation part. Go on.
Okay, so after that, now I will explain how our Python code implements these ideas and how we interpret the visuals. So first of all, the data processing through our code. Our code reads the combined data set, cleans textual inconsistencies, converts product prices to numeric values, extracts years from months column, and organizes the data by category. It then constructs the city month pivot table, fills missing values using column means, and then normalizes each row to produce the final 12D vectors, as you can see on the screen. All these steps are described in detail in our report, and the data extraction script is referenced there as well. So moving on, I'll talk about the cosine similarity matrix. So we computed a full city cross city cosine similarity matrix. The diagonal is always 1 because each city is identical to itself. The off-diagonal values reveal patterns. And as you can see in this heat map, exactly as I said, the diagonal values are always yellow, and yellow color indicates very high similarity. And on the other hand, the blue and green color indicates lower similarity. As you can see, like some of the colors are green, some are light green, some are aqua, and the color that is most darker, which is like the dark blue color or the violet color, it indicates those two cities are the least similar to each other. So yeah, like moving on in the food staples and grains category, similarities range from 0.97 to 0.99, showing strong coordination across cities. In the network graphs, if we take the tall example 0.8, So if we use tau is equal to 0.8, we extracted the strongest inflation relationships. The graph becomes sparse enough to visually detect clusters. For example, Rawalpindi, Sargodha, and Bahawalpur form a highly interconnected group. And Karachi behaves differently than interior Punjab due to port-driven pricing structures. Cities like Khosdar or Larkana form interesting bridges between clusters. And yeah, like moving on, now I'll talk about the centrality measures. So to understand influence within these networks, we computed degree centrality, closeness centrality, betweenness centrality, and lastly, eigenvector centrality. So talking about the degree centrality, it tells how many strong links a city has, and the closeness centrality is how close a city is to all others, and betweenness centrality tells how often it lies on on shortest paths. And lastly, eigenvector centrality, it tells the connectivity to already influential cities. And if I talk about in food staples and grains, Rawalpindi and Sargodha had the highest degree and closeness, which means that their price pattern represent our national trends. Furthermore, Bahawalpur and Khosdar had high eigenvector scores, which means they are connected to cities that are highly influential themselves. Uh, and lastly, Karachi scored slightly lower because of unique market behavior. And these results match the interpretations in our report as well, which you can see on the screen. These results match the interpretations. And now, like if I talk about other categories, for example, for fruits and vegetables, the price behaviors are more volatile. And yes, and now and you can see the centrality shifted towards Faisalabad, Gujranwala, and Sialkot. And our Pindi's influence reduced because perishable goods have region-specific patterns. For meat, poultry, and dairy, Larkana, Faisalabad, and Rawalpindi emerged as the dominant cities. And this suggests that livestock supply chains vary significantly from grain markets. And lastly, the topic which I will be covering is the temporal Hasse diagram. So our Hasse diagram shown in the report, as you can see on the screen, it reveals that in 20, from 20 that basically 2023 and 2024, their network becomes stronger as they are linked closely. And 2025 breaks the chain, which indicates structural change. This could be due to supply shocks, inflation spikes, or year-to-year anomalies. And basically, that concludes the computational and visual analysis. And now I would like to call my teammate Taha Jabbar to describe the weighting schemes and overall city influence.
Okay, thank you, Sharam. Now I will discuss the weighing schemes, the overall influence ranking, and I will also be the concluding what we did in this project. So since each centrality captures different characteristics, we combine them using three schemes, three weight schemes. First of all, we used equal weights. Every metric, degree, closeness, betweenness, eigenvectors get gets weight 0.25. This treats all measures as equally important. Second, we used correlation-based weights. Metrics that are highly correlated with others get lower weight because they provide redundant information. Metrics with unique patterns get higher weight. This reduces bias in the final ranking. And thirdly, we use entropy-based weight. Metrics with more variation across cities get higher weight. If betweenness is almost identical across all cities, it contributes less. We also assign weights to different categories. For example, we assign 0.25 weight to food staples, 0.20 to utilities, and 0.15 to transport. This reflects real-world household importance as documented in our report. Combining metric weights and category weights give us a final influence score per city per year. Now let's talk about the interpretation of overall influence score across food staple, fruit, vegetables, and different categories. As you know, Rawalpindi consistently ranks highly strong alignment with the national inflation patterns. Faisalabad, Gujranwala rise in perishable goods sectors, and Larkana shows a strong influence in meat dairy networks. This multi-layer analysis reveals that city influence is not universal. Each category paints a different picture, and weighted aggregation is essential for fairness. Now let's talk about the conclusion, what we did in this project. Our project demonstrates how discrete mathematics transport raw CPI data into a structured insight. 12-dimensional city vectors capture monthly inflation behavior. Cosine similarity identifies cities with matching economic patterns. Threshold similarity graphs reveals clusters and outliers. Centrality measures quantify each city's role and influence. Weighted scoring synthesize multiple measures across categories. Hash diagram shows how city relationships evolve year to year. The final outcome is a replicable mathematical framework that can be used for economic analysis in any multi-city or multi-year dataset. Our report documents every step of this process thoroughly. And that was all our project. Thank you for listening us.